Hello everybody, my name is PC Gamer and today is a special day. It's the, yesterday was the 7th year anniversary of my YouTube channel and I thought of doing something special. As you can see, this isn't Minecraft nor World Tanks. This is actually the setup I am using to measure the speed of light in air, and today I'm gonna go over it. So, how I'm measuring it, there's two different ways. This is the first way. This is basically brute forcing the speed of light. So this is the setup we're using. Basically a laser. This is a Torlabs NPL64B laser that shines along this path, bounces off of these mirrors, and at the beginning of the laser path, we put a beam splitter, as you can see there, that splits the beam into two. That goes to one diode, as you can see right there, and that diode is connected to this oscilloscope, and then it travels a certain distance and then goes into diode number 2 right there, and it goes in the oscilloscope. Now what we see on the oscilloscope is that when the laser, I forgot to mention, this is a pulse laser. Right now it's set to 1 megahertz, so every second it oscillates a lot, so it produces a lot of pulses. And this is one of the pulses. As you can see, this is from the first diode. It goes in here, and then since it takes a bit of time to travel all of this distance, as you can see here, when the second diode receives a pulse, there's a bit of offset, which we'll call delta t. So what we do with it is that then we take our cursors and we set it on the peaks, and then we note down the difference in time, called here delta t, let's say y1, and then this will be distance x1, the distance between the two diodes. And then what we do is that we take this diode, we put it somewhere else, and then the delta t will change, and we'll call it y2 and then x2. And just do this, like, I think we did it 12 times. My team and I, this is a team of 4 people, and so then you plot x2 minus x1 and then y2 minus y1, and that gives the speed of light in air. It's 1.0003 factors off from the speed of light in vacuum, if I recall. Don't remember how many zeros, But yeah, so this is it, and now I'm going to show you how it works. So this is it. This is the laser. Torlabs NPL64B. We set it to 1 megahertz, as you can see, and we put the pulse width to minimum. This is a 50 milliwatt laser, and right now I'm not wearing my goggles, but that is because we have a neutral density filter in here. Basically a piece of glass that is OD2. OD2 is the 2 means it decreases the intensity of the laser by a factor of 100. So I am now not wearing my glasses because it's perfectly fine, but the problem with it is that, well, since it attenuates the laser intensity so much, you cannot see anything on the oscilloscope anymore. So now everything is aligned. It took us a lot of time, but now that's aligned. I'll put on my goggles. As you can see, these are OD3 rating, and the goggles basically remove everything that's red. So this is red. This is black now, and it's focusing on my glasses. But so let me put on my goggles. All right, goggles are on, and take this off. This is the filter, and it has a small screw. You unscrew it, you take it out, and now the laser is shining. I cannot see I cannot see it with my goggles, but using the phone, you can probably, look, the purple dot, you can actually see the laser light, right there, in the middle of my finger. I cannot see absolutely anything with my goggles, but the phone can still see, and bam! So this is the pulse as sensed by the diode. Oh, I should say the diode used is an FDS 010 by Torlabs. It has a 1 nanosecond rise time. and it's here. And this one is the second diode. And how we take the difference between the two is that we take our cursor, we turn on the cursor, and then cursor A, we put it at the first peak. I think that's good. And then we go to cursor B by pressing, and we go to the second one. I mean, it was already aligned. And as you can see, the difference in time is, oh, I was blocking the laser, but it's 42.8 nanoseconds, right? Now, what if we take this laser and we'll put it here, like along this path? So what if we take it from here, put it here, which will be much closer from the first diode? So let's do it. I mean, usually we screw it down, but just for demonstration's sake, I didn't. And as you can see, this is around the line. Could be better, I'm just eyeballing it now, but bam, it's different. This was where it was before, now it's here. So if we take cursor B and align it, and now we have another distance, which is 22, I mean, another time difference, which is 22.2 nanoseconds. But the nice thing about this oscilloscope, the Regal DS1102E, is that right here, the time scale is now 5 nanoseconds. So each small graduation here, small square, is 5 nanoseconds. But this one can go much bigger. So if we, now we put it to 2 nanoseconds, and you cannot really see it anymore, can you? So how you measure the distance here, this is much more accurate, but you put the peak on cursor 1 here. So this is 8.88. Let's estimate to be 8.9 now. And then you take this and then you put it on the second peak. And the second peak, oh, sorry. Oh, so sorry about that. The cursor is actually at 2.4 nanoseconds. And if we put it on the second peak, this is 24. So 24 minus 2.2, no, 2.4, it's 21.6. So yeah, this is how you do it more accurately. If you put it to 5 nanoseconds. And this is basically it. I mean, we just finished taking the measurement, so we don't have the speed of light yet, but it's probably going to be around plus minus 1%. So we expect it to be between 2.96 to the power of 8 meters per second to about 3.02 times 10 to the 8 meters per second. And and for the distances, this is actually a pretty nice table because every single hole is exactly 1 inch apart. So yeah, this was the speed of light using a laser. And now let's move on to the second part. Oh, and nice thing, it has a key. Look, bam. All right, I'm just gonna leave it like this. I'm gonna come back to it later, because to safely do this, you need to make sure that I also need to put back on the neutral density filter here, because yeah, it's I mean, it's safer to have it on, because if someone were to turn it on and someone wasn't wearing goggles, it wouldn't blind that person. Plus, you gotta come back to put the caps on this. And anyways, this is it. And now let's move on to the, one final thing. This is actually not a very good way of measuring things because, well, you're basically brute forcing it, and right now we are limited by the oscilloscope. This is a 100 megahertz one. And I don't know if you saw, but when I was moving the cursor, it was jumping by 0.08 nanoseconds. So you cannot get more accurate than that, which is why we are expecting a 1% inaccuracy. Well, I mean, the inaccuracy in this is big enough so that all of our measurement issues, we're probably going to be off by like a millimeter each time. They won't make an impact because the light travels at around 1 foot per nanosecond. So 1 millimeter difference is not going to change anything on this. But a smarter way of measuring the speed of light would be of using a Michelson interferometer, which is basically a laser, shines through a beam splitter, light comes here, comes back, light comes here, comes back, and then when it comes back, because these distances are different, when it comes here, it actually creates a pattern of this kind, where the black spots represent destructive interference, and the white spots represent constructive interference. So destructive interference is that when you have two waves, let's say 1 and 2, and they're perfectly out of sync, they will the combination of these two will just be a flat line along the x-axis. So you won't be able to see anything. But let's say that they're perfectly aligned. Now the output of this will be the exact same thing. Like the period will stay the same, but the output will be the sum of the two waves. Right, so you see this, and by varying this mirror by a slight distance, these pattern will change, right? So if you move it this by, let's say 50 turns, and you have a way of measuring how much distance your mirror change, you can count the number of fringes appearing, and then you can get your wavelength. And since you know the frequency of this, if you find the wavelength of this, you can find the speed of light that way. So now let's move on to the second part. Oh, let's see, everything's closed. Yes, let's put on the cap. All right, so let's move on to the second part, which is measuring the speed of light using coaxial cables. So this is a pulse generator. Oh, this is going crazy. All right, so this is a function generator. I mean, a pulse generator. It just produces pulses, not functions. But and the coaxial cables basically transport electromagnetic waves, and they actually have a velocity factor, which depends on their electrical permeability. I think. Yeah. So they don't travel at the speed of light in here. They travel at a certain velocity factor for RG58 cables, which are these. They have 50 ohms impedance, but it travels at 0.66% the speed of light. No, 0.66 of the speed of light, which is 66% the speed of light. So when we know that, what we can do is send a signal here, and then here, the signal will continue through this wire, but then when it reaches the end of the wire, there's no connection. So what happens is that the wave bounces off, and then the wave travels back all the way in here, and then comes back here, and bam, it displays it. So this is one pulse, as you can see. But when you zoom out, I mean zoom in actually. Oh, this is when you zoom in, as you can see, there's two pulses. Right here, two big pulses. And these pulses are what I just described. So the signal comes here from the signal generator, I mean function pulse generator. So it displays here, and then the signal travels all the way here to the end of the cable, bounces back, and comes here. So how do you calculate the speed of light using this method? So once again, you use your cursors. So you have cursor A. It's not on, so cursor, all right. Cursor A, you put it on the first peak, and then you take your cursor B by pressing it. Oh, sorry, I wasn't filming. Sorry about that. So as I was saying, you take your cursor A, you put it on the peak, and then you click, and you get your cursor B, you put it back on the peak, you put it on the other peak right here, and then bam, you have a difference, bx minus ax, 27.6 nanoseconds. And since you know the length of this cable and you know the velocity factor, you can calculate it pretty easily. I don't have a pen and paper with me, so you can write it down. I might do it with the part of editing. I don't know how much I'll edit this video. I haven't edited videos in years, but yeah, so this is it. And you can also change the length of the cable, which I can't really do one-handed. Let's see, what should I... Okay, I'll put this cable. I think this is a... Okay, so this is 25 feet. so we should see a rather large delay. So these are some really annoying connectors. You need to push and twist. So if I put it here. All right, so as you can see, where's the second peak? Well, the time distance, the time delay is much greater because this is 25 feet and it gotta go back and forth, right? So it's 25 feet, 50 feet in total. And if it was in air, it would travel at 1 foot per nanosecond. But the velocity factor in here is slower, so it travels at 0.66 feet per nanosecond. So if you have 50 feet traveling at 0.66, it's what, around 80? It's around like 80 to 85 nanoseconds. So if we have that estimate, we can measure it by taking the cursor. Wait, let's see. Does it display if I... look, it displays. Let's move it down so it doesn't get eclipsed by this thing. Okay, so if we take cursor B, we move it on the peak, and then take cursor A and move it on the other peak. And this is a difference of 77.20 nanoseconds. So as you saw, I think the other cable was like 10 to 15 feet. I don't remember which one, but yeah. Oh no, the other one was 10 feet. I forgot. Yeah, exactly 10 feet, and this one's 25. And as you can see, the delay increased. And once again, if we plot this on Python, we get the speed of light. And we actually finished the data taking with these, and we got the speed of light that was off by maybe like 0.5% or so, which once again is because of the inaccuracy in the oscilloscope. Because as you can see, for example, first off, the peak. How do you know where the peak is? For example, if I go on B, what if the peak is here? Just, well, moving the other way, but let's say it's here, right? Just slightly off, right? This tiny off factor, if you see BX, goes from 77.2 to 77.4. It's a 0.2 nanosecond jump, right? It's huge inaccuracy. As for the second one, which is why usually you don't want to brute force this kind of stuff. And this is the function generator side of things. This is actually a much easier setup. We took the data in like an hour or two, including measuring all of these cables, fixing our bugs and everything. So, but this one, well, this one took a lot more. So first off, we were supposed to use a Pascal laser and mirror and everything set up, but turns out it didn't work. And it did work, but it didn't want to modulate. Modulating a laser means making it pulse and making its output, changing its output to fully function, right? So right now we're modulating the laser to do this. So there's a pulse, goes down. There's a pulse, goes down. Right? The Pascal laser, what happened is that we're trying to put a square signal in it at 2 megahertz. But the thing with that laser is that its rise time and its fall time, which is the time for the laser to turn on and the time for the laser to turn off, were very long. So what happened is that the output looked like a sine wave, like this. But we were looking for a pulse wave, like as we saw here. So by doing this, it was almost impossible to measure. It was very off. It wouldn't even display correctly. It would change a lot. So then we had to move on to another laser. This one was what was available, but as you can see, this is a class 3B laser. So we had to do our laser certification. And I have my laser certification now, so Maybe we'll see more laser content on this YouTube channel in the future. Maybe. But so yeah, we moved on to this. And then we took the measurements. And then we went home. And then the next day, everything was misaligned. And that is because we're trying to align the mirrors perfectly to shine the laser over the distance of 12 meters. But what happened is that on the other side of this wall, there's construction. And all the vibration made it so that the mirrors were slightly moving out of alignment every day. And today we basically took every single data point in a row. Took maybe 3 hours, realigned everything, and yeah, this is it. So thank you guys for watching. I'll upload more videos in the future because it's almost my summer break. I am now much better in World of Tanks and Minecraft. So yeah, thank you very much for watching. This channel is now 7 years old, quite a lot. And if you guys want me to go more in depth, I will on like these measurements. I am very happy to do so. And yeah, just thanks for watching, and goodbye.